Question 6 shows a graph of a Maxwell-Boltzmann distribution of some gas, one single gas, at two different temperatures. That's important. It says the graph below shows the distribution of molecular speeds for a gas at two different temperatures. Which statement is correct? First, real basics on how to read one of these graphs. You look at the peak. So this first curve number 1, shows the gas, whichever this gas is, and you see the peak of this graph. Draw a line from the peak down to the x-axis, and we can just say this is clearly a relatively low speed. So it's about the location of the peak, whether it's shifted left or right, not the height of the peak. So although this peak is higher than the second curve, the location of the peak is shifted most toward the left. The most probable speed is shifted more toward the left. Looking at the second curve, that was not a great trace. Let's try this again. We see that this second curve has a peak around here, and that's going to be a higher speed. The higher probable speed for this particular temperature. A couple of concepts to note. First of all, regarding temperature, the speed increases with an increase in temperature. So speed increase, temperature increase. That means, of course, that higher temperature means higher speed. We know already from just this information that the second curve represents the higher temperature. So curve number 2 is the higher temperature. You're not looking for the highest peak. You're looking for the peak that is shifted most to the right. So if I were to draw in an even higher temperature, let's say I were to take this gas and ramp up the temperature to a third higher temperature, it would look even more flattened out. Maybe not like that, but look more flattened out like this. So when the temperature goes up, the curve gets flatter and flatter, and the peak shifts more and more to the right. If I were to draw in a super cold version of this gas, so like if I took this gas and turned the temperature way down, the peak would be high and then be very shifted toward the left. That's how you read them. Now, knowing this information, we can go through and see that the first curve is clearly the lower temperature. So from that information, we see that the first curve represents the gas at the lower temp. That's true here and here. It's not true that it's curve 2 being the lower temperature. But what about the effusion rate? The effusion rate is related to the molar mass of the gas, but it's also related to the temperature. So we have a second concept that the Maxwell-Boltzmann distribution graphs can show us. One is temperature and the other is molar mass. We'll talk about molar mass if that question appears. But in this case, it makes sense that if the temperature is higher, it's moving faster, and therefore it will have the higher effusion rate. So the higher temperature is going to be the second curve. It will have the higher effusion rate. You can think of effusion just being the movement of the gas in basic terms. Higher effusion rate, higher temperature, because it's moving faster. So curve 1 is going to be the lower temperature, that's true. But because of that lower temperature, it is moving more slowly and is not going to have the higher effusion rate. It is going to have the lower effusion rate because it has the lower temperature, because it's moving more slowly. So your answer is going to be this last one here. Keep in mind that Maxwell-Boltzmann distributions can also be related to molar mass. So if you have this curve and this curve, let's call it curve A and curve B. And they are two different gases at the same temperature. So let's say it's the same temp. So same temperature, but A and B are two different gases. One gas has a higher molar mass than the other. All you've got to recognize is the same general principle that curve A, the peak of curve A is shifted more to the left, so it's going to be the slower one. And then the peak of curve B is shifted more to the right, so it's going to be the faster one. And when it comes to molar mass, think about the fact that heavier molecules move more slowly. So this the curve with the shifted peak most to the left is going to be slower, and it's going to be the heavier gas with a higher molar mass. The faster gas the one with the peak shifted more to the right, will also be the lighter gas, the one with the lower molar mass. And all of this here is simply just in case you get a problem where it's talking about molar mass and the distributions rather than the temperatures. So there are two concepts that are similar but not exactly the same. Question 7. The volume of the gas in a balloon is 25 degrees Celsius, and the volume changes from 0.800 liters up to 2.45 liters. So as you're reading these problems, make note of the variables that you come across. What is the resulting final temperature? So you're looking for the final temperature. This means you're looking for T2. What was given is T1. Of course, every single time you see a temperature, you need to turn it into Kelvin. I know that Celsius is given and all the answer choices are given, but mathematically this is only valid with Kelvin because Kelvin is an absolute temperature scale. So you might have to, in this case we will have to, turn the temperature given into Kelvin, work with it mathematically in Kelvin, and then turn it back from Kelvin into Celsius. You cannot just use Celsius as it's given. So let's add 273. So 25 plus 273, that's going to give us 298. So the initial temperature is 298 Kelvin. We have our initial volume, we have our final volume, and we want to know what the final temperature is. This is Charles's law. Charles's law says that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. That's one way you can write Charles's law. Or if you prefer to kind of derive them all from the ideal gas law equation using that same methodology, we have P1 V1 equals N1, R is always the constant, T1, all over P2 V2 equals N2 R T2. We have the initial conditions and the final conditions. This balloon undergoes some change. Now, of course, we need to cross out everything that is constant. So pressure wasn't mentioned. Oh, actually, it was mentioned, but it's constant, so perfect. So we can cross out pressure. It's a balloon, so we assume that it's a sealed balloon, and the number of moles of gas in the balloon are not changing. R is also constant. So getting rid of all the constants, we have, well, this stuff is going to go, all this stuff is going to go. What we have here is just another way to write Charles's law. Remember, if you were to put, right now we have all the V's on one side and all the T's on the other side, that's valid. You could also see it written out as I had it the first time with all the 1's on one side and all the 2's on the other side. It doesn't matter. Mathematically, these are equal. If you don't believe me, you can solve them for yourself. I'm going to stick with the top one because that one came directly from what most professors seem to want, which is like derive it from the ideal gas law equation. The math will still math if you're right. Let's plug in everything. The initial volume was given as 0.8 liters. We don't know the final temperature. We know the initial volume though. We know the final volume, which is given here as 2.45. The initial temperature in Kelvin is 298. And we don't know the final temperature. So use your cross multiplication skills, do 298 times 2.45, divide that by 0.800, you get 912. Some questions may ask you to determine the temperature in Kelvin. Be very careful. The numbers are different enough where we don't really care about rounding. I'm just going to put a 0.6 Kelvin. But of course, if you subtract 273, then you'll get the temperature in degrees Celsius. So let's do that. 639.6, so about 640. So 640 degrees Celsius is your answer. Main way to avoid messing up on questions like this that involve temperature, always put it in, always put the temperature in Kelvin when you work with it mathematically. Number 8, the ions calcium and magnesium are present in groundwater, and you can remove them by pre-treating the water with what? You're probably going, I'm not sure if you have to memorize the solubility rules, but if you do have to memorize the solubility rules, memorize the solubility rules. But the solubility rules will tell you how you can remove calcium and magnesium, because calcium and magnesium are going to complex with the anion. So note that these are both cations, right? They're both positively charged, so they're cations. Cations are going to pair with anions in double replacement reactions. So when that happens, you remove these cations when they pair with an anion to produce an insoluble product. So double replacement reactions in general look like this. You have AB, so that's some ionic aqueous solution. And you mix it together with CD, and you get AD plus CB, where A and C are the cations, and then you have B and D, which are the anions. And notice how they switch the cations that they're with. In a double replacement reaction, typically when it comes to this kind of stuff, move that this way, move this way, you'll typically have it look like this. You'll have an aqueous solution, so you have like the ions dissolved, and you have another aqueous solution, and you mix them together, and you'll get a precipitate, which is going to be the insoluble product, and the other one will typically be aqueous still. So in this case, this right here is the solid. It's the one that's insoluble per the solubility rules in this generic example. And since it's insoluble, it is the precipitate. This question can seem a little confusing, and it is. So let's kind of go through each answer choice and see what makes sense. So calcium chloride is soluble. Based on how to read the solubility rules, it's a common chloride. And the only time that chlorides are not soluble is when they're paired with like the silver or the lead 2 or the copper 1 or the mercury 1 ions. So calcium chloride would totally be soluble, as in you could put it in your water, it would dissolve, and then hopefully make a insoluble product to pull the calcium and magnesium out. But that doesn't really seem to make much sense, because if you're trying to remove calcium and magnesium, why would you add something that already has calcium in it that clearly is soluble? It won't remove the calcium. Also, the chloride ion, any of them that pair up with the magnesium ion, will still be soluble, and it won't actually remove either of them. So calcium chloride dissolved into the water that has these ions in it won't actually remove the calcium or the magnesium, because you don't get an insoluble product. Calcium chloride will just make more calcium chloride, or you might even get some magnesium chloride, but neither of them are insoluble. So this answer choice does not make sense. Now let's look at lead 2 sulfate. Lead 2 sulfate, according to the solubility rules, it's a sulfate, and those are soluble, yay. Unless that sulfate is paired with lead, in which case this is. So lead sulfate is not soluble, which means that you can't put it in your water to remove an ion, because it won't even break apart in order to get the job done. So lead 2 sulfate would not be a good option, because it itself is insoluble, so you can't really put it in water to remove something to create another insoluble product. It won't break apart into ions. Now let's look at sodium carbonate. Sodium carbonate itself is a carbonate. So we go down here. Carbonates are not soluble. That sucks, right? Carbonates are insoluble unless that carbonate is with something from group 1, which sodium is in group 1. So it turns out that sodium carbonate is soluble. Because it's soluble, you could expect to dump it into your water and it would break apart into those sodium and carbonate ions. So you get some Na plus ions, you get some CO3 2 minus ions, and then you have to ask yourself, okay, well clearly the carbonate ions are going to pair up with the calcium and the magnesiums. Are carbonate ions going to create something insoluble that you can pull out of the water? Let's see what happens here. If the carbonate ion pairs with the calcium 2 plus ion, you get calcium carbonate. And if the carbonate ion pairs with the magnesium 2 plus ion, you would get magnesium carbonate. So now you want to check the solubility of magnesium and calcium carbonate. They are still carbonates. So it says here, carbonates are insoluble. That's good because you want that precipitate to form so you can pull it out of your water. Um, and it says carbonates are soluble when they're with group 1 things or ammonium. Calcium and magnesium are not ammonium, and they're also not in group 1, they're in group 2, which means that these are going to be insoluble precipitates. So these are insoluble, and they are precipitates, just like we want, because that's what you want, right? You want to pull the calcium and the magnesium out of the water. And just from experience, you will eventually learn, and also from the solubility rules, that nitrates are very, very soluble, and there are no exceptions that we care about. So potassium nitrate is soluble, which means that um, any possible nitrates, so potassium nitrate is soluble. So any possible nitrates, if you were to form calcium nitrate, is it soluble? Yes, it's not going to form a precipitate. Same thing with magnesium nitrate. All that to say that if you were to pair this anion with calcium or magnesium, it's still going to be dissolved in your water. If you were to pair this anion with calcium or magnesium, they will still be dissolved in your water. And if you were to pair the sulfate ion with calcium or magnesium, you can't, because the thing that you're trying to add won't even break apart in the first place. So the only thing that makes sense is the fact that sodium carbonate will dissolve in water, and when it does so, it'll pull calcium and magnesium ions out of the water because the products of carbonate pairing with calcium, insoluble. The product of carbonate pairing with magnesium, insoluble. So that's kind of how you read and do that kind of question. Number 8, it says the beaker below represents a solution of barium chloride with the given molar mass. If each particle represents 0.050 moles, what mass in grams of the compound was dissolved? So let's take some notes from dimensional analysis, which will always be helpful, and recognize that there are, well, first of all, you have to identify which particle is which. The chloride ion is going to be -1, so that's going to be these things there. And then the barium ion is going to be +2, so barium 2 plus. And using dimensional analysis, we can see that, well, there are 6 particles, 1, 2, 3, 4, 5, 6, of chloride. So for every one particle, we just said that each of them is 0.050 moles. So using dimensional analysis, we cancel out particles, and we have moles, and 6 times 0.050 is there are 0.3 moles of the chloride ion. Let's do that same logic for the barium ion. There are 3 particles of barium, and every one particle is 0.050 moles still. And we're going to simply get half of that, so it's going to be 0.15 moles of the barium 2 plus ion. Where particles cancel, we have moles. Once you have that information, then you can combine them to figure out how many grams of the total particles there were, or how many grams of the total solute that was dissolved in this solution. So we see that we have moles of chloride ions and moles of barium ions. You can actually use either one of these to get the right answer. So here's how I'm going to do it with the barium ion. So if we have 0.10 or 0.15 moles of the barium 2 plus ion, we can convert our moles of that barium ion into moles of the barium chloride from which it came. And for every 1 mole of barium chloride, we get 1 mole of barium ion. And that makes sense because if you look at the little subscript next to the Ba, you don't see anything because there's 1. There's 1 barium ion for every 1 package of barium chloride that it comes from. That makes sense. So moles of barium ions, convert that to moles of barium chloride. And then, of course, just going to do a molar conversion from moles of barium chloride to grams of barium chloride using the molar mass, 208 for every 1. And that would give you your answer, which is about 31 grams of barium chloride. What if you decided to use the chloride ion? Well, the same thing would apply. You have 0.3 moles of the chloride ion, convert your moles of chloride ion into moles of the barium chloride from which it comes. And this is where the fixing happens, so to speak, because for every 1 mole of barium chloride, you get 2 moles of chloride ion. So we have moles of chloride ions cancel, and then you can go from the moles of barium chloride to the grams of barium chloride, and we get that 1 mole is still 208, because now we're looking at barium chloride, and we still get about 31 grams of barium chloride. So this particular question seems kind of tricky at first, but just count your number of moles for each one, or count your number of particles, convert them to moles using dimensional analysis. They weren't kidding when they said dimensional analysis is useful at the beginning of the year, because it really is a problem-solving strategy for situations like this. And notice how 0.15 times 208 gives you your answer, and 0.3 divided by 2 is 0.15. You're still multiplying that by 208 and you still get the same answer. So it doesn't matter which one of these you use, you still should get the answer of 31 grams of barium chloride. And question 10. Calculate the molarity of the chloride ions in a solution in which 78 grams of vanadium 3 chloride is dissolved in enough water to make 260 milliliters of solution. So this one's only tricky because notice how it says the molarity of the chloride ions. If this is completely soluble, you will get 1 vanadium 3 plus ion for every 3 chloride ions in solution. So actually, I probably should write that as a dissociation equation. So let's say you have VCl3, and it dissociates into vanadium 3 plus and 3 chloride ions. So the molarity of the chloride ion should be 3 times more than what you would typically get from here. So let's do the math for it. We have 78 grams of VCl3 over 1. Let's convert that into moles immediately. So VCl3, 2 moles of VCl3. The molar mass is given to us as 157 grams per mole. This is how many moles of VCl3 we have. But notice how, just like we saw with that barium question, for every 1 mole, actually I'll put the units first. So VCl3, we're going to convert that into moles of the chloride ion. If this is completely soluble, then for every 1 mole of the vanadium 3 chloride compound, we get 3 moles. That's right, there's an invisible 1 here. For every 1 mole of the vanadium 3 chloride compound, we get 3 moles of the chloride ion. And then that's going to give you how many moles of the chloride ion you have. So let's do the math there. We get 78 times 3 divided by 157. I got 1.49 moles of chloride ion. That's step 1. Once you figure out the moles of chloride ion, then you need to figure out the molarity. Remember, molarity is equal to moles of the particular solute, in this case we care about moles of the chloride ion, divided by the liters of the entire solution. Now we know that there's 260 milliliters of solution, so remember your conversions, 260 milliliters. Convert that from milliliters to liters, which basically means you divide by 1,000, and I'll actually put it this way. So doing your substitutions, you get that the molarity is going to be equal to the number you just got, 1.49 moles of the chloride ion. Divide that by the total volume of the solution, which is 0.260 liters, and that's going to give you your answer. And we get about a molarity of about 5.73 molar. Now that's related to the chloride ion. That's the molarity of the chloride ion, not the molarity of the vanadium ion. The vanadium ion molarity is 1.49. But remember, there are 3 times as many chloride ions, so there'll be 3 times the concentration of chloride ions than vanadium 3 ions. And that's why your answer is 5.73 molar. And the last one we'll do for this section of the video How many molecules of air are in a bicycle tire that has a volume of 1.60 liters at 27.5 degrees Celsius and 6.45 atmospheres? So we have a ideal gas law problem. We assume that everything is going to be an ideal gas law problem, ideal gas, unless you talk about it otherwise. Um, Ideal gas law is PV equals nRT. And looking at our information here, we have a volume, we have a temperature, and we have a pressure. We want to know molecules of air. Remember that P is pressure, V is volume, N is moles, not grams and not molecules, but you can convert. R is R, and then T is T for temperature. So sometimes it's helpful to kind of list out the variables this way, and the constant in this case. So the pressure is 6.45 atm. The volume, it's in liters, which is good. It's 1.60 liters. We don't know the number of moles, so I'm going to leave that as blank. Moles of air. We know R has a couple of values it could take. There's a 8.3141, there's a 0.08206, or you can also just round it to 821. And the units for that are atmosphere liters per mole Kelvin. That's the R value you need to use, because checking out your units, we want atmospheres, good. We have liters, good. We have moles, well, we will have moles. And we have Kelvin, which is also slightly problematic, but we can fix that here. Remember that that temperature needs to be in Kelvin, so 270 or 27.5 plus 273-ish is about 300.5. We're not really worried about sig figs right now, and that's Kelvin. The rules of math are going to make you solve for N, right? To do that, you'll get that the moles is equal to PV over RT. And that's simple enough to do. Pressure is 6.45, the volume is 1.60, R is 0.0821, and then T is 300.5-ish. And you'll get, it's like really step 2. I guess you can call it like step 1, set it all up. Step 2, solve for N. When you do this, you get 6.45 times 1.60 divided by the sum of, or the product of these. I got about 0.418 moles of air. Now that's a very convincing number. You know, whenever somebody made this test, they're like, oh, what if somebody were to put 4.18? That's convincing, but it's not the answer. Step 3 is you need to convert your moles into particles. Actually, I'll move that down here. So dimensional analysis along with Avogadro's number, we have 0.418 moles of air. And we convert that from moles of air into molecules. It doesn't matter that it's air or whatever, because a mole is the same number regardless of what it is. 1 mole of anything is 6.022 times 10 to the 23. And that's going to give you your answer. This question could have also asked the mass of air if you were given the average molar mass of air. We are asked about number of molecules, which means it's going to be a huge number. And all of these huge numbers should give you a clue that it's going to relate to Avogadro's number. So multiplying it out, we get about 2.52 times 10 to the 23 molecules of air, which is this answer here.